In the silent depths of space, a giant waits, for a million times heavier than our sun. It swallows everything that comes near, even light itself. Hidden at the heart of our galaxy, this invisible monster controls the dance of more than 400 billion stars. Tonight, we journey into its shadow, where time slows, space bends, and a single star must race at 17 million miles per hour just to survive. When you look up at the night sky, the stars seem scattered and free. But that freedom is an illusion. Every one of those countless suns, along with planets and gas clouds, moves in a perfect cosmic dance around a hidden center. Even our solar system races through space at over 500,000 miles per hour, taking 240 million years to complete one galactic orbit. The last time Earth was here, dinosaurs ruled the planet. Something unseen binds all of this together with unimaginable gravity. But what? For centuries, astronomers believed it was simply the pull of all stars combined. But the math didn't add up. Stars on the galaxy's outer edges were moving far too fast. By all logic, they should have drifted away into space long ago. Something far more massive was holding them in place. Something invisible, yet millions of times heavier than our sun. Imagine iron filings swirling perfectly around a magnet hidden beneath a table. You can't see the magnet, but you can see its power. Our galaxy behaves the same way. The invisible center lies toward the constellation Sagittarius, but thick clouds of dust hide it from ordinary telescopes. For decades, this cosmic fog kept it secret, until scientists used radio waves, a form of light that can pierce the dust, to finally look inside. In the 1970s, astronomers turned their radio telescopes toward the galactic core and made a shocking discovery: a compact, powerful source of energy brighter than anything else in the Milky Way. They called it Sagittarius A, the asterisk marking something unique and extraordinary. It poured out more energy in a second than our sun releases in a year, yet remained invisible in every other wavelength. A roaring cosmic engine that could not be seen. This mysterious signal came from a region no larger than our solar system, yet it outshone entire clusters of stars. No visible light, no gas cloud, no shining disk, only radio waves, constant and unchanging. The source was stable, massive, and utterly dark. Whatever it was, it didn't behave like a star, a gas cloud, or anything known. Something new and terrifying lurked there. By the 1990s, astronomers began tracking stars orbiting this hidden object using infrared telescopes. The results were astonishing. Stars near the center were racing around empty space at incredible speeds. One of them, known as S2, completed a full orbit every 16 years, around nothing visible. At its closest approach, it traveled at 17 million miles per hour, skimming past a point of total darkness. The math was undeniable. Only an object with a mass of 4 million suns could grip these stars so tightly, yet occupy a region smaller than our solar system. No cluster of stars could survive such density. Only something far more compact and extreme. S2's orbit became the ultimate test. Its path proved that this was not a swarm of stars or debris, but a single, colossal object. As it swung close to the dark center, the star's light stretched and reddened, exactly as Einstein's theory predicted near a black hole. Time itself slowed in its presence. At last, the mystery was solved. The heart of our galaxy is ruled by a supermassive black hole, an invisible monster holding everything in its gravitational grasp. Known as Sagittarius A, it sits 26,000 light-years away, shaping the Milky Way's destiny. The stars orbit it, our solar system circles it, and perhaps one day, everything we know will fall into its endless shadow. If you could compress 4 million suns into a space smaller than Mercury's orbit, you'd create the gravitational heart of our galaxy. But sheer mass wasn't the only clue. Size was the key. As star S2 raced close to this invisible object, its survival proved the center must be smaller than 120 astronomical units across. Packing that much mass into such a tiny region defies the limits of normal matter. Even the densest neutron star material would collapse under its own weight. The conclusion was undeniable. Only a black hole could exist there. Other nearby stars confirmed it. One, named S4714, swooped within just 12 astronomical units of the center, about the distance of Saturn from our Sun, moving at nearly 5% the speed of light. Every observation pointed to a single truth. The Milky Way's core was home to a region where matter and energy vanished beyond the point of no return. For decades, Sagittarius A remained unseen. Astronomers could measure its mass and detect its radio signal, but no one had ever seen it. Then, in 2022, that changed. Using the Event Horizon Telescope, a network of 8 observatories across 4 continents, humanity captured the first image of our galaxy's black hole. The array acted like a telescope the size of Earth, powerful enough to spot an orange on the moon. Even so, photographing Sagittarius A was a near impossible task. It's far smaller than the black hole in galaxy M87, only 4 million solar masses wide, with an event horizon just 12 million miles across. And we view it through 26,000 light-years of dust and gas, a cosmic fog that distorts every signal. To overcome this, astronomers gathered data over multiple nights in 2017 and spent 5 years processing it with supercomputers. The result was breathtaking, a glowing ring of orange light surrounding a perfect black circle. That dark core marked the event horizon, where space-time curves so steeply that nothing can escape. The image matched Einstein's century-old predictions precisely. The swirling plasma reached temperatures of 10 billion degrees, twisted by immense magnetic fields, rotating clockwise at nearly the speed of light. This image was more than a scientific triumph. It was proof. For the first time, we saw a black hole. The shadow of Sagittarius A confirmed that our galaxy's heart is a true gravitational abyss, a place where the fabric of reality collapses. Nearby, the star S2 continues its furious race, the fastest known orbit around any black hole. During its 2018 close pass, it reached 17 million miles per hour, crossing the equivalent of the United States in a fraction of a second. Despite the crushing tidal forces that could tear ordinary matter apart, S2 survived. Its immense density kept it intact as it sped just 120 astronomical units from the black hole's edge. At that distance, space itself bends violently. Light from S2 is redshifted as it climbs out of the black hole's gravity, photons losing energy, turning redder and dimmer by the time they reach Earth. Even time slows down. Clocks near Sagittarius A tick more slowly than those farther away. If you stood on S2 during its closest approach, your time would lag behind the universe outside. You'd feel nothing unusual. Your body and mind would slow equally. Yet to distant observers, you'd appear frozen in slow motion. Einstein's theory had predicted this a century ago. Near a black hole, time itself bends. And now, through these racing stars and that haunting ring of light, we've witnessed the truth. The Milky Way's heart is not just darkness, but the very edge of time itself. At Stu's closest approach to the black hole, time itself begins to twist. For every million seconds that pass on Earth, Stu experiences about 999,999. The difference, barely 10 seconds, seems insignificant, yet our instruments can measure it. This subtle slowing of time, known as gravitational time dilation, grows more extreme the closer one moves toward the event horizon. If you could somehow hover just outside that invisible boundary, your seconds would stretch into hours for an outside observer. From their perspective, you'd appear frozen in place, fading slowly into red light before vanishing. But from your own view, you'd cross the horizon in an instant, falling deeper toward the singularity. Two realities existing at once. A paradox that defines black hole physics. Even the gas swirling around Sagittarius A feels this distortion. Material near the event horizon moves through time more slowly than gas farther out, creating the complex motion patterns astronomers captured in the first image of our galaxy's central black hole. But time dilation is only the beginning of the strange effects shaping this cosmic monster. In the calm world of Newtonian physics, orbits are simple, perfect loops repeating endlessly. But near Sagittarius A, space itself bends those rules. The star known as S2 doesn't retrace the same path each time it swings around the black hole. Instead, its orbit slowly rotates, tracing a graceful rosette in space, a phenomenon called orbital precession. Each 16-year journey draws a new petal, forming a cosmic flower unlike anything in our solar system. This subtle shift, just 12 arc-minutes per orbit, about 1/5 of a degree, may seem tiny. Yet detecting it pushes modern telescopes to their absolute limits. The gravity collaboration combined 4 8-meter mirrors in Chile's Very Large Telescope, creating a virtual instrument with the precision of a 130-meter wide lens. Their measurements matched Einstein's predictions exactly, confirming that general relativity still holds true even in the extreme gravity near Sagittarius A. This rosette dance also reveals what isn't there. If hidden masses or dark matter surrounded the black hole, they would distort S2's path. The near-perfect match to Einstein's model tells us that Sagittarius A dominates its realm completely, an island of gravity alone in the dark. Most of the time, our galactic center sleeps quietly. But 2 centuries ago, something woke it up. X-ray echoes bouncing off nearby gas clouds reveal that Sagittarius A erupted in a violent feeding frenzy around the early 1800s. For a brief moment, it blazed millions of times brighter than normal, outshining entire clusters of stars. Think of it like a dying campfire suddenly flaring when someone tosses fuel onto the embers. The radiation burst outward at light speed, striking molecular clouds that still glow today from the echo of that ancient light. The timing is perfect. Those reflections are only now reaching Earth, a silent message from the past, proving that the monster once stirred. Astronomers believe the awakening was triggered by a massive gas cloud, or perhaps the remnants of a shattered star, drawn too close to resist. The result: a temporary accretion disk burning with temperatures of billions of degrees, releasing torrents of X-rays and high-energy particles. Traces of that storm still shape the strange filaments and structures we observe near the galactic core. Today, Sagittarius A rests once again, despite its immense power, for a million times the mass of our Sun. It consumes matter with surprising restraint. Each year, it swallows roughly the mass of Earth. That sounds colossal, yet compared to its size, it's barely a sip. At this rate, it would take trillions of years to double in mass. Our galaxy's heart may seem calm now, but history reminds us that beneath that silence lies unimaginable energy, waiting for the next spark to awaken the sleeping giant once more. The gentle nature of Sagittarius A comes from the strange physics of accretion near black holes. Matter doesn't simply fall straight in. It must first shed energy and angular momentum through chaotic interactions of magnetic fields, radiation, and turbulent gas. NASA's Chandra X-ray Observatory revealed a surprising fact. Less than 1% of the gas captured by Sagittarius A actually crosses the event horizon. The rest is superheated and blasted back into space through violent outflows, a cosmic filter that lets only the tiniest fraction slip through. This inefficiency explains why our black hole glows faintly compared to the blazing cores of distant galaxies, whose central giants consume matter at furious rates. Because Sagittarius A feeds so slowly, our galaxy avoids the chaos seen in active galactic nuclei. No colossal jets, no galaxy-wide storms of radiation. But this calm won't last forever. In about 4 billion years, when the Milky Way collides with Andromeda, torrents of gas and stars will rush toward both galactic centers, igniting a feeding frenzy that could transform our quiet black hole into a brilliant quasar. For now, though, it remains a peaceful giant, powerful enough to anchor our galaxy, yet gentle enough to let life thrive in its orbit. Its restraint shows the delicate balance between gravity, magnetism, and thermodynamics, the subtle forces shaping the cosmos. From Earth, the Milky Way looks like a soft band of light arching across the night sky, steady and eternal. But its elegant spiral form exists only because of the massive gravitational heart at its center. Sagittarius A doesn't simply sit there. It sculpts the very architecture of our galaxy. Gravitational waves ripple outward from the core, compressing gas and stars into bright spiral arms, much like traffic bunching along a busy highway. Magnetic fields, twisted by the black hole's rotation, stretch thousands of light years, guiding energy and matter through vast galactic circuits that sustain structure for eons. This central anchor also acts as a kind of cosmic metronome. Subtle shifts in its gravitational field send rhythmic pulses through the galactic disk, triggering waves of star formation that spread outward like ripples across a pond. Astronomers have discovered a deep link between supermassive black holes and their host galaxies. The larger the black hole, the more massive the galactic bulge. Sagittarius A's just right mass places the Milky Way in a cosmic Goldilocks zone, stable, balanced, and capable of nurturing complex structures like our solar system. Too large, and our galaxy would have become a compact, quiescent spheroid. Too small, and it might never have formed its elegant spiral arms at all. But our black hole doesn't dwell alone in this crowded region. Within just 3 light years, astronomers have identified thousands of stellar objects, dense remnants, neutron stars, and even other black holes, each orbiting within this extreme gravitational cauldron. In 2004, scientists discovered CERS 13E, an intermediate mass black hole roughly 1,300 times the mass of the Sun, accompanied by 7 massive stars. It orbits Sagittarius A like a cosmic moon, proof that smaller black holes can survive and even thrive in the monster's shadow. Such systems reveal how giants like Sagittarius A may have formed, through countless mergers of smaller black holes drawn toward the center over billions of years. Today, the galactic core remains a dense, dynamic realm, home to exotic remnants and violent interactions. Some objects swing perilously close to Sagittarius A, their surfaces torn by tidal forces, unleashing brief flares of X-rays before vanishing again into the shadows. It is a place of destruction and creation intertwined, the quiet heart of chaos that holds our galaxy together. The crowded heart of our galaxy is a place of chaos and creation. Here, stars, black holes, and neutron stars drift dangerously close to one another, sometimes forming binary systems that spiral together, releasing ripples through space-time itself as gravitational waves. Amid this turmoil, astronomers have found something unexpected: clusters of young, massive, blue stars shining brightly near Sagittarius A. Their existence defies logic. Conditions this extreme should tear gas clouds apart before they can form stars. The only explanation is that these stars were born farther out and later migrated inward, drawn by the powerful gravity of the galactic center. This cosmic metropolis, teeming with ancient remnants and newborn giants, forms one of the most extreme laboratories in the universe. And sometimes, the monster at its core reminds us of its power. For most of human history, Sagittarius A has slept in silence. But on May 13, 2019, it suddenly awakened. Astronomers at the Keck Observatory watched in astonishment as the black hole's brightness flared 75 times stronger than usual. Within 2 hours, it blazed like one of the brightest stars in the sky. The outburst released more energy in a few hours than our sun emits in several years. The likely culprit was a gas cloud called G2, drawn too close and shredded by tidal forces. As the fragments spiraled inward, they formed a temporary accretion disk, glowing at billions of degrees and racing around the black hole at nearly a third the speed of light. Using radio interferometry, scientists watched hot plasma orbit Sagittarius A in real time, completing full revolutions in just minutes. These violent flares reveal how space and time twist near the event horizon. Light bends, stretches, and beams in strange patterns predicted by Einstein's equations. And though the 2019 flare was the most dramatic, smaller bursts happen regularly, proof that our galaxy's heart is far from dormant. Then came the moment humanity did the impossible, photographing the darkness itself. In 2022, the Event Horizon Telescope captured the first image of Sagittarius A glowing ring of light encircling a perfect shadow. That shadow marks the event horizon, the boundary beyond which light, time, and even information cannot escape. From Earth's distance of 26,000 light-years, this vast structure, 12 million miles across, appears smaller than an orange on the moon. The ring's brightness isn't uniform. One side glows brighter because matter there races toward us at near-light speeds, its light amplified by relativity. Creating this image took 8 synchronized radio telescopes across 4 continents, forming a virtual Earth-sized lens. Thousands of terabytes of data were combined over 5 years, refined through complex algorithms that accounted for atmospheric distortion and light bending around warped spacetime. The result perfectly matched Einstein's predictions: the shadow's size, the glowing ring, even the direction of the black hole's spin. The image not only confirmed general relativity, but revealed the true scale and mass of Sagittarius A with extraordinary precision. To look at that shadow is to stare into the edge of the unknown. The event horizon is not a surface of matter. It's a boundary in space-time where escape becomes impossible. Step beyond it, and every possible future leads to the singularity at the center. Inside, space and time trade places. Falling inward becomes as inevitable as the passage of seconds. Nothing, not even information, escapes that darkness. The moment you cross the horizon, your story, your data, your light, your very existence vanishes from the universe forever. This is the ultimate mystery of black holes. Objects that erase everything they touch, yet shape the galaxies that give birth to stars, worlds, and life itself. Sagittarius A is both destroyer and creator, the silent heartbeat of the Milky Way. The event horizon size depends entirely on a black hole's mass. Smaller black holes span only a few miles, while giants like Sagittarius A stretch across distances greater than planetary orbits. Paradoxically, as black holes grow, their average density decreases. A stellar black hole compresses immense mass into a tiny space, but Sagittarius A's density is comparable to water. As mass increases, the volume expands faster, making supermassive black holes less dense than their smaller cousins. Yet, density becomes meaningless at the horizon itself, the place where classical physics breaks down completely. Beyond it lies a realm where logic, cause, and time itself dissolve. Approaching Sagittarius A brings tidal forces beyond imagination. Just as the moon's gravity pulls Earth's oceans, the black hole stretches and squeezes everything in its grasp. At first, the difference between the pull on your head and feet would seem small, but as you descend, it intensifies exponentially. You'd be stretched lengthwise and compressed sideways into a thin, fragile thread, a fate scientists call spaghettification. For small black holes, This destruction happens long before you even reach the event horizon. But around Sagittarius A, the process is gentler. You could cross the horizon without instant death, though the deeper you fall, the stronger the pull becomes. Eventually, even the atoms of your body would tear apart, though over minutes, not moments. This same force rips apart entire stars that drift too close, creating brilliant flares as their material spirals inward. These death spirals form temporary disks of glowing gas that can outshine galaxies for years. But reality near a black hole isn't so simple. It depends entirely on your point of view. Imagine watching someone fall towards Sagittarius A. To you, they slow down, grow redder, and fade, frozen forever at the edge. Their image flattens into an invisible, two-dimensional shell, an effect physicists call pancaking. Yet to the falling person, nothing seems unusual. They pass smoothly through the horizon, feeling only the gradual pull of gravity. Both perspectives are correct. In the warped fabric of space-time, truth becomes relative. The person both crosses and never crosses the horizon, both stretches into infinity and freezes in time. This paradox hints at a deeper mystery. If all falling matter appears compressed at the horizon, could the black hole's surface itself store the information within it? This idea inspired the holographic principle that the universe's three-dimensional reality might be encoded on two-dimensional boundaries. But then arises the question, if two versions of you exist, one pancaked at the edge and one falling inward, which one carries your consciousness? The answer remains hidden. Until physics unites quantum theory and gravity, the true nature of this paradox, and of reality itself, will remain one of the greatest mysteries in the cosmos. And at the heart of it all, Sagittarius silently waits, the keeper of secrets and the destroyer of certainty. The information paradox grows more mysterious when we consider Hawking radiation itself, a faint, random glow that seems to carry no trace of what once fell into the black hole. It's like trying to rebuild a burned library from the heat and smoke that remain. Yet, the conservation of information is a law of quantum mechanics. Breaking it would shatter the foundation of physics itself. Scientists have proposed several daring solutions. The holographic principle suggests that information never truly enters the black hole. Instead, it's encoded on the event horizon's surface, the entire interior becoming a kind of projection, a cosmic hologram. Another idea proposes that infalling matter stays quantumly entangled with the Hawking radiation escaping outward, allowing information to leak back into the universe. Others envision a firewall of energy at the boundary, a quantum inferno that burns anything approaching, preventing information loss altogether. Some of the boldest theories suggest spacetime itself is born from quantum entanglement. In this view, the black hole's interior isn't a place at all. It's a network of quantum connections that encode every detail of what has ever fallen inside. If true, even the faint, random-looking Hawking radiation might secretly preserve the full history of the black hole's past. For Sagittarius A, this mystery isn't just theoretical. Hidden within it may be the record of every star and gas cloud devoured over billions of years, perhaps waiting to be read by civilizations far in the future. But unlocking that story means solving physics itself. Hawking's discovery in 1974 changed everything. He showed that black holes aren't eternal prisons. They slowly evaporate. Near the event horizon, virtual particles pop into existence. One falls in, the other escapes as real radiation. Over unimaginable timescales, this process drains the black hole's mass, like ice melting under starlight. Smaller black holes radiate heat. Giants like Sagittarius barely glow. Its temperature is a few trillionths of a degree, colder than the cosmic background itself. For now, it absorbs more energy than it emits. But trillions of years from now, as the universe cools, it will begin to fade. That fading will be slow, beyond human comprehension. Sagittarius A will take about 10 years to evaporate completely. Only in its final moments will it unleash a titanic flash, brighter than billions of suns, releasing every atom it ever consumed in one cosmic heartbeat. Yet Hawking radiation reignited an even deeper paradox. If this radiation carries no information, then quantum mechanics fails. New theories suggest the information might be hidden within delicate correlations between the emitted particles, a secret code written in light. But solving that code creates new contradictions. Entangled particles near the event horizon face a choice: stay linked to their infalling partners or to previously emitted radiation. Quantum physics forbids both, leading to what's now called the firewall paradox. The only escape may be to sacrifice one of physics' sacred principles. Perhaps the event horizon isn't smooth, as Einstein believed, but a blazing wall of energy that annihilates anything crossing it. Under the firewall theory, Sagittarius A would appear calm from afar, yet anyone approaching it would meet instant, fiery destruction. This paradox exposes the rift between quantum mechanics and gravity, two flawless theories that refuse to agree. String theory and loop quantum gravity offer glimpses of a resolution, but none complete. For now, the firewall remains both a warning and a mystery, proof that even in the age of modern physics, the universe still hides secrets deeper than our understanding. From our everyday view, space and time seem fixed, distances stay constant, triangles add to 180 degrees, and parallel lines never meet. Yet near Sagittarius A, these basic truths collapse. The fabric of space-time twists so deeply that reality itself bends beyond recognition. Einstein's general relativity showed that massive objects warp space-time like heavy spheres pressing into a stretched sheet. Gravity isn't a pull, but motion through this curved geometry, and near a supermassive black hole, the curve becomes extreme. Light that should move straight bends into circles around Sagittarius A, creating a cosmic mirror hall where one star may appear in multiple places at once. This gravitational lensing magnifies and distorts the universe behind it. Time, too, loses its uniform rhythm. Near the black hole, clocks slow compared to those far away, until, at the event horizon, time nearly stops. Around rotating black holes, space-time itself is dragged along, pulling even light into its spin. This frame dragging reaches far beyond the horizon, twisting gas clouds and stars across the galactic center. Closer in lies the photon sphere, a region where light can orbit endlessly. If you could hover there and look sideways, you would see the back of your own head, light from your face looping around the black hole before returning to your eyes. Even the shadow of Sagittarius A is an illusion of warped light. Gravitational lensing makes it appear more than twice its true size, magnifying the darkness against the glowing accretion disk, a cosmic mirage captured in the first historic image. These distortions are not just strange, they're vital to physics. Black holes test Einstein's equations under conditions no laboratory can reproduce. But they also stretch time itself to its breaking point. As matter falls toward the event horizon, time slows dramatically. From far away, objects seem to freeze at the edge, their light reddening and fading as they approach. A falling astronaut's final heartbeat would appear to last for centuries. Their last thought could unfold across millennia. Each photon escaping this gravity well loses energy, its color stretching from visible light to radio waves miles long. Eventually, the infalling image fades into darkness, yet never truly vanishes. To a distant observer, every object that ever approached Sagittarius A remains frozen at its edge, leaving a ghostly imprint in space-time. If we could observe with perfect precision, we might still see the first stars that fed this black hole billions of years ago, suspended in an eternal fall. From outside, a black hole never seems to finish forming or evaporating. Time near its surface stretches so infinitely that its end can never be witnessed. Inside the event horizon, the story changes. Crossing the boundary feels ordinary. No wall, no flash. Yet escape becomes impossible. The laws of space-time direct every path inward, making the fall as inevitable as time itself. Within, space and time trade roles. Moving toward the center becomes as unavoidable as moving forward through time. The deeper you fall, the stronger the tidal forces grow, stretching, pulling, and distorting everything toward the singularity, the point where all known physics breaks down. As you fall deeper into Sagittarius A, the faint microwave glow of the Big Bang transforms into a searing storm of radiation. From your perspective, the universe outside fades, while the cosmic background ahead grows blindingly blue-shifted and hot enough to vaporize any matter long before reaching the singularity. Inside the event horizon, time loses all meaning. You still experience it normally, but your connection to the external universe is severed. No signal or message can escape. Causality itself breaks. Whatever you discover within this abyss, new laws, new dimensions, even new realities, will remain forever locked away. Some theories imagine that the black hole's core could link to other universes through wormhole-like bridges or lead to distant parts of our own cosmos. But these ideas, however elegant, can never be tested. The event horizon seals them beyond reach, a one-way journey into the unknown. At the center lies the singularity, where space-time, matter, and mathematics collapse into infinity. Here, general relativity admits its own failure. Density and curvature soar beyond limit, and equations lose meaning. It's like dividing by zero. The math breaks, and so does our understanding. Yet most physicists believe infinity is not real, but a sign that our theories are incomplete. Quantum physics likely prevents true singularities. In string theory, particles have finite size, stopping infinite compression. Loop quantum gravity suggests space itself is granular, imposing a smallest possible scale. These ideas hint that the core of a black hole might not be a point of nothingness, but a region where space-time bends, folds, or transforms into something new, perhaps preserving information in unknown quantum states. Still, without a full theory of quantum gravity, the heart of Sagittarius A remains beyond human comprehension, a boundary not of space, but of knowledge itself. Yet even this cosmic titan will not last forever. Trillions of years from now, when all stars have burned out and galaxies are dust, Sagittarius A will still linger, slowly feeding on the darkness. But as the universe grows older and colder, even black holes will begin to fade. Through Hawking radiation, they lose mass at an almost imperceptible rate, until, after 10 years, Sagittarius A itself will vanish. For most of that eternity, it will seem unchanged, but in its final moments, it will erupt in one last burst of unimaginable energy, releasing everything it ever consumed, stars, planets, dust, back into light. By then, the universe will be near absolute zero, vast and silent. The final flash will fade almost instantly into the cold dark. What remains will be a sea of scattered particles drifting endlessly through expanding space. No stars, no galaxies, not even black holes. The monster that once anchored our galaxy will have completed its cosmic cycle, born from the death of ancient stars, dying in the farthest reaches of time. Sagittarius A stands as a reminder. Even the mightiest force in the universe must one day yield. In the end, gravity itself bows to the deeper laws that govern existence, proving that nothing, not even darkness, lasts forever.